few announcements before we get started, just to get everyone up to speed with any of the upcoming due dates. As I mentioned, all you had to worry about homework-wise before Mardi Gras break was the homework on sets, which was due that past Friday. I had the homework on counting principles due, originally that was going to be due tomorrow. I did push it back a day, just in case anyone had any questions about it. We can talk about it on Wednesday when we meet up. So the counting principles, I pushed that back a day, and I believe the quiz has been pushed back a few days as well. So if you put those in your planner or something, or you had those noted, just keep in mind I changed those. Besides for that, I also have assigned a new set of workbook pages. Workbook number 3 up here. Make sure you write those down. It's due this Friday. And in case you can't read it, it might be kind of small, but it's page 10, numbers 1, 2, 3, and 4. Page 11, numbers 1 and 3. And that's workbook number 3. So this is sort of contingent upon hopefully you receiving the workbook by now, since we're pretty good majority of the way into the semester by now. So yeah, that'll be due this coming Friday. So the 2 assignments, one due Wednesday, a quiz due Friday, workbook due Friday. I think that's pretty much it. Miss anything? Does anyone have any questions? Anything at all? So if not, then let's go ahead and get started. So we're going to pick up where we left off. We were talking about counting before. So yeah, we were talking about mainly the multiplication principle. And with the multiplication principle, we were talking about when do you, well, how many dashes do you put? What numbers do you put in those dashes? And do you divide by all ones, or do you divide by 1, 2, 3, 4, all the way up until you hit the number of dashes you had? And really, for the remainder of this section, we're just going to do problem after problem to really emphasize this idea. So it's just going to be a collection of different problems that go off of that same idea, starting with example 7 here. So we will start this off. There's a combination lock on a suitcase that has 4 wheels, each labeled with the 10 digits 0 through 9. So from here, we can ask how many 4-digit combinations are possible if no digit is repeated. And so you can hopefully visualize, maybe you've seen a suitcase like this before, the various tumblers or anything like that. A lot of bike locks come with this. In fact, for those of you in class, my backpack comes with it, and I've never been able to figure out what it does. I don't know what the code is. I don't know what this does. Anyone knows? I'd love to find out. I have no clue. But anyways, 4 wheels, the numbers 0 through 9 are possible. And we're going to first figure out how many 4-digit combinations are possible if no digit is repeated. So for whatever problem we have dealing with the counting section, we always want to approach it by thinking about how many dashes do we draw, and what numbers go into the dashes. So I guess that leads us to the first question, how many dashes? So does anyone have any idea how many dashes? It's just 4. And hopefully it wouldn't be the 10 digits. So it's going to be 4 dashes. We have a dash for each wheel. So it's a dash for each wheel. And so the question is, what numbers go into these? So really this goes into the number of options we have for each wheel, with keeping in regards to any conditions they ask of us. So the first wheel. Well, the first wheel, there's no restrictions. We have all 10 options. It's just 0 through 9. That's 10 options. So let's start it off pretty simply as 10. So let's say we choose one of the numbers. I'll do an example off to the side just so we can kind of visualize this. So this would just be an example of a combination we choose. Let's just say 4. That's the first number we chose. Well, no digits repeated. So they ask that we do not repeat a digit. So the next number better not be a 4, but it can be anything else. How many options is that now? It's 9. That's 9 options. So go straight into 9. So we can choose another option, 7. And then, again, no digit can be repeated. So 4 can't be chosen, 7 can't be chosen. That leaves us with 8 options. I think you might see the pattern from here. There's 8, and then there's 7. So an example, 4, 7, 3, and then maybe 6 or something. But that would be an example. And you can write off examples off to the side if it helps you visualize what a certain option may look like. Sometimes it's good to just break down a problem to a specific case or specific example. It might help you visualize things better. But now that we have this, so remember what we talked about last time. I know it was over a week ago, but we also talked about, does order matter? Because if order matters or doesn't matter, we have to do a completely different thing for that. So in this situation, all right, so try to think about this. Does order matter in this situation? In this context, do you think order matters? Order matters? Order does matter. And I can convince all of you why this is the case. So order matters, if anything. Order definitely matters. I'm going to explain why order matters. So I know with iPhones, you normally unlock it. Well, I guess there's the face recognition and everything, but for those of you who had or still use the 4-digit PIN, imagine if your PIN was 4736. If order did not matter, then I can get into your phone by typing in 7346. That doesn't make, it seems like that doesn't make any sense, right? But if order doesn't matter, then as long as I just figure out the 4 digits of your passcode, then that means I can get into your phone. So order does matter because each one of those numbers has significance being in that particular place. If your password's 1234, then if I were to be able to get into it by typing in 4321, then that implies order doesn't matter. So that's an example I commonly refer to emphasize that order does matter in this situation. Each wheel of this combination is specific. Even if we can't really give it a label like we talked about before, but each one of these are specific. And so when order matters, as we already established, let's detour right fast. When the order is important, we just divide by ones. When the order matters, we just divide by ones. 1, 1, 1, and 1. That's whenever the order matters. Order matters means that we put these ones here. And so now it's just 10 times 9 times 8 times 7, which we can do pretty easily, I hope. Ten times 9 times 8 times 54. So that's how many combinations there are if you allow no repeats. Okay, so you have a 1 out of 5,040 chance of guessing it right on your first try. There's a few attempts. So what about if you want it to be even harder to crack? What about if you allow the opportunity for digits to be repeated? Okay, well, what does that change? So from digits not being able to be repeated to now they can be repeated. there's going to be some significant overlap between part A and part B. Well, there's still 4 wheels. I think we can all agree there's still 4 wheels. What are the numbers that go into the wheels, or at least in these slots? It's just going to be 10 every time. It's going to be 10 every single time. The reason why we went down before was because we couldn't allow any repetition, which meant each time we picked a number, that was one less number we can choose for the next available wheel. Now we can allow every option. There's no restrictions. So you could pick 4, 4, 4, 4 if you wanted to. For some people, they really like their passcode to be 0, 0, 0, 0. Although probably not the best choice, it is a repetition that is perfectly permissible for iPhone passcodes. But does that change the relevance or the importance of the order? Of course not. Order still matters. Order still matters in this context. Because again, you can have 4, 3, 4, 3, and then someone could type in 3, 4, 3, 4 and get into your phone. That wouldn't be very secure. Those need to be different passcodes entirely. So order still matters, which means we divide by ones again. Make sure that's just 10,000. Does anyone have any questions up to this point? Okay, and now part C is probably the trickiest one. How many 4-digit combinations are possible if successive digits must be different? What does successive mean?
Following.
Yeah, it's the immediately following digit. So let's think about an example of this. Maybe break it down a little bit. So if I choose my first number, just say let's make the first number 8. So the first number is 8. That means the immediate next digit cannot be 8. So I'll make it, let's make it 4. Well, the immediate next digit cannot be 4, but it can be 8. Successive just means the immediate next one. So this one could be 8 again. It doesn't say repetition is gone. It says that in other words, it's saying that you can't have duplicates immediately next to each other. That's ultimately what it's saying. That's kind of what the successive term is referring to. So you can have duplicates, they just can't be right next to each other. And then the next one, it could be anything. You could have made it 4, make it 5. So that just helps us visualize what's going on here. So it's not saying that no repetition's allowed, it's just saying that next digit better not be the previous digit. And so what does that change about this problem? Well, still 4 wheels, still just 4 wheels. And then, what are the numbers that go into these positions?
The first one's still going to be 10.
Yeah, the first one doesn't have any restrictions against it.
And then all the other ones are going to be 9.
Yeah, so all the other ones are going to be 9. Just think about that. All the other ones are going to be 9. The reason why that is, you choose the first one, there's no restrictions on the first one. It can be whichever one of the 10 digits you want. The next digit can't be the previous digit. The previous digit means we lose 1. That's 9. Okay, so I wrote 9 there. The next digit cannot be the previous digit. Not the one before it as well, just the previous one. So that's just 1, again, that we lost. It's still 9. And then the next one cannot be the previous digit, which again is 9. That's why it is 10 times 9 times 9 times 9, which is 7290. Is that it? Okay. Yeah, 9 to the third power is 729. Throw in a 0. And I think I already jumped the gun because you divide these by ones because the order still matters. So part C is probably the trickiest part of this, and that's just really interpreting what successive means and how that will immediately affect the numbers that go into the slots. Does anyone have any questions before I move on to the next problem? If you didn't, please write down the workbook assignment, which I'll probably send out an email later re-emphasizing this. No, let's go ahead and move on. An identification code is to consist of 3 letters and 3 digits. Determine the following. How many codes are possible? Okay, so an identification code is to consist of 3 letters followed by 3 digits. How many possible codes are there? Just like with any other problem, we start off with trying to figure out how many dashes we put. Does anyone have any intuition on this one? It's 6. We're putting 6. It's 3 letters, so it would be 1 letter, 2 letter, 3 letters, and then the 3 digits. Think about it as this problem is pretty similar to like license plates. 3 letters and 3 digits. I'm pretty sure Louisiana did that for the longest time, and then they switched because they ran out of combinations. But so 3 letters, 3 digits, 6 dashes in all. And then we need to figure out what numbers go into each one of these. Well, are there any restrictions? It doesn't say anything about repetition, so I feel like it's pretty, well, that's pretty open. We'll go into the first slot. It'd be 26. Remember, the first 3 are letters. How many letters can you choose from? All of them. How many letters are there? 26. It's 26. So if we wanted to write an example off to the side, first letter could be, I don't know, a J. Next letter, just, well, the next one is a letter. I kind of gave that one away. And again, there's no restrictions. It doesn't say get rid of repeated ones. It just says any letter. So 26 again. And 26 again. So any letters. They can be repeated. They don't have to be. Doesn't matter. Now it's on to 3 digits. Because remember, the next 3 dashes represent the digits. So how many digits are there?
10.
It's 10. Don't say 9. I've seen this in a lot of other classes. I know you mean to say 10. A lot of people just think, oh, it goes up to 9, so there's 9 digits. 0 counts as 10. I've seen it happen a lot. So just make sure you remember there's 10 digits. It's 0 through 9. Again, a lot of people read 9 and think there's 9 digits. It's an honest mistake. Just make sure, keep that in mind. And then since there's repetition, you just have 10s to complete it because the remaining ones are digits. So this could be maybe 5, 5, 8. Something like that would be an example of something. You can have repetition, so that completes this part. That's the dashes, the numbers that go into the dashes, and then the order. So in this case, does order matter? order matters. So imagine if some fool escapes the police and he had a license plate of exactly what I wrote. And then you have a license plate that is PBJ855. Well, they would type in JPB, the person who got away. They would pull up PBJ855 and then see your license plate because order wouldn't matter in that situation, which means you'd be going to jail. Maybe a silly example, but this is to emphasize that the order matters. Each license plate is different, even if you just simply try to switch around the letters and the numbers. This is what we call permutation. It's kind of a cool buzzword. But order matters. So order matters, which may look familiar, because that means we're going to populate all the denominators with ones. A lot of multiplication follows. And once we put all of this into the calculator, really it's just 26 raised to the third power. 10. Really, it's just the same thing, just saving time. But it's this big number. And again, you shouldn't, in this section, get any decimals. This is a section that's completely based off of discrete answers. Whole numbers, countable numbers, simple numbers. It might get kind of grotesque in terms of their magnitude, but that's still okay. It just means there's a lot of combinations. There are a lot of combinations here. So Louisiana, the state of Louisiana, used to have 3 letters followed by 3 digits. And that means they went through 17.5 million combinations before they switched the 2. Does anyone have any questions? Just a reminder, if you're on your phone, you're working the next problem. Just keep that in mind. All right. So in continuation of part A, part B says how many of these codes contain no repeated letters and no repeated digits. So now they're being a little bit picky here. So how many of these codes contain no repeated letters, no repeated digits? So what aspect of this problem does this change in relation to the previous part? Well, there's still 3 letters, still 3 digits. I think it's safe to assume we're going to stick with the 6 dashes. Still the 3 letters, the 3 digits. Contain no repeated letters and no repeated digits. Okay, so now we need to think about what numbers do we have available, or, well, numbers in terms of options. So here, we're starting off with the letters. It's the 3 letters first. We start off really with all 26 available to us. That part doesn't change. But if we choose the first letter to be, say, B, it means we can't repeat B. We can't use B again. There's no repetition, which means instead of 26 letters, we're down to 25. I think you see where this is going. There's 25 letters, which means you have to choose another one, say W. And then once you take out B and W, down to 24. Oh, do not get in the habit of just putting 23, 22, 21. I've seen that happen before. Because remember, it's only those first 3 spaces that correspond to letters. The next 3 are digits. So you have to use numbers that correspond to digits. So what would go in the next space? It'd be 10. Leave it 10. But you can't repeat the digits. So you go from 10, you use one of them, you can't repeat it, 9 left. Well, now you use 2 letters. Can't repeat them, 8 left. And then finally, we figured out the dashes, the numbers that go into them, and then the order. Does the order matter? Of course it does. Still matters. One, 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 one. Six times 25 times 24 times 10 times 9 times 8. Rather large number to represent a rather large quantity of combinations. 1, 1, 2, 3, 2, 0, 0, 0. Okay, is everyone good up to this point? So it's just gonna get a little bit more difficult from here. Part C, how many different codes are possible? The repetition of letters is permitted. Okay, so we can repeat letters. We can't repeat numbers. And the first 3 entries must all be the same letter. Okay, that's quite a decent amount of restrictions to process. So if anything, let's just think about it in terms of the 3 things we've been doing. Dashes, numbers in the dashes, order. Is any of this information going to affect the 6 dashes we've had in the previous problems? No, it doesn't. Here it's still 1, 2, 3, 4, 5, 6. It's still the 6. And some multiplication is going to happen. Okay, so let's try to process this. Repetition of letters. So let's focus on letters first. What's everything that talks about letters? You can repeat letters. The first 3 entries must all be the same letter. That's everything I see in the problem that refers to letters. With this information, does anyone happen to know what the first 3 spaces, what you got, John?
26, 1, 1.
Yeah, so this one's pretty interesting. Did you take 105 last semester? Okay, just wondering. Pretty common problem. 26, so let's break that down. 26, because the first letter can be anything you want. No restrictions on the first letter. But it says the first 3 entries have to be the same letter. So if we think about our little example off to the side, whatever your first letter is, let's say I choose L, then the next 2 letters have to also be L. That means you have one choice for the next 2, no matter what, which is why it's 1 and then 1. You have to choose L and then L. So repetition is permitted, which fine, we have repetition of L's, and then the first 3 entries have to be the same letter. So hopefully that's fine so far. And then now we move on to the digits. So then it goes on to say repetition of numbers is not permitted, and that's it. Okay, so the repetition of numbers is not permitted, so you can't repeat the numbers. So how many digits can you choose from? It's the 10, but you cannot repeat, which means once you pick one, you lose one, and then you lose another one after you pick that one. 8. So then that could be 8, 7, 6. And then we ask ourselves, does order still matter? It still matters. The restrictions do not change the context of the problem in terms of how this order may or may not affect things. So guess what happens? We get a bunch of 1s. So really this comes down to 26 times 10 times 9 times 8. 18, 7, 20. Let's do one more. How many different codes are possible if the first letter must be an A, a B, a C, or a D, and repetition is just not permitted at all? So again, they're giving restrictions which should not affect the number of letters and digits in the problem. So from here, now we need to figure out, all right, where do the restrictions come into play? How does that pertain to, start off with just the letters. The first letter must be an A, B, C, or D, and repetition is not permitted. So what about this one? Does anyone have any intuition on what the first three blanks would be for this one?
I know the first one would be 4.
First one is going to be 4, because the first letter, A, B, C, or D. First letter has to be one of those 4. So one of those 4, you have 4 options for the first one. What about the next one?
25.
It's 25. A lot of people put 3 because you're used to that I suppose, dissension of numbers following, but it doesn't say that the second letter has to be one of those 4 letters or the third one. It's just saying that the first letter, you get 4 choices, but the next letter, it just cannot repeat. Just cannot repeat. So it's 25. And then it's 24. So that one's a little tricky, no doubt. That one's a little tricky. It's 4 for the first one. We have 4 options, but then the next one is 25. Because one of the 4, whichever one you choose, can't be repeated, but you can choose from any of the letters now. And repetition is still not permitted, so we move on to the digits. 10, 9, and 8. That's pretty standard from the ones before. Since you can't repeat the digits, you can choose from all 10 of them. And then since you can't repeat, you lose 1, and then you lose 1 again. Order still matters. So we divide by all ones. 4 times 25 times 4, 10 times 9 times 8. 1728000. And so we are here. Does anyone have any questions about this problem? It's, I guess, in its full scope before we move on. Not. Let's go ahead and move on. Okay, so example 9, there's some electronics store. They receive a shipment of 40 of the calculators. 4 of the calculators are defective. And then they choose 4 of any of the 40, could also include the 4 defective ones, but 4 calculators are randomly selected to be sent to a local high school. And then they're wondering how many selections could be made in part A. So, using all this information, we start off with the number of dashes. How many spaces are we allocating? What's that?
4.
Yeah, hopefully it's not 40. So it's definitely going to be 4. You can use that intuition. I know some math problems are a little crazy, but hopefully not that crazy. Only 4 dashes. But my question is, where is this 4 coming from? Is it coming from that 4 or that 4? The first one or the second one? It's definitely the second one. So just make sure, it's just a coincidence in this problem that there's 2 4s, but it's the ones that are being sent. So make sure we keep that in mind. So how many selections can be made? So now the question is, what numbers go into these spaces? So, well, if anything, I think it's clear what goes into the first one. 40. Any of the 40 calculators. The defective information that they give us is irrelevant for part A. Part A does not ask about defective. It just doesn't care. You might foreshadow part B, but we'll get to that one momentarily. How many selections can be made? 40. And then what about the next one?
39.
Yeah, it's 39, not 40 again, because you can't send the same calculator twice. So there's no repetition here. And the problem didn't need to say there's no repetition. You instinctively knew from the context of the problem that, well, you can't repeat the calculators you send. And so you keep that going. So notice we haven't even used the defective information at all. And that's part of the trickiness of this problem. We're doing that on purpose, throwing a few numbers at you to see how you can process the numbers and the context for which it plays a role in. And then the question is, so we're going to multiply these together no matter what. The question is, does order matter? Order does not matter. I don't care which calculator I get first. You're still sending me a shipment of 4 regardless. Order does not matter. I think that's the first one we've gotten today. Order does not matter. So what does that mean for the denominators? So we think back to what I explained before Mardi Gras break. That means you start with a 1, the bottom right, 2, 3, 4. You just keep counting up by 1 until you run out of spaces. And also something I talked about last time that I want to emphasize is try to do this in the calculator the way I'm about to do it. Try to put it in the calculator like this as you see it. It's not going to be correct. So let's fix that. This was something I talked about last time. Notice these numbers are different with the implementation of parentheses. The reason why the calculator doesn't know when the numerator ends and when the denominator begins. So all it's doing is, it's in the first entry I put, it puts every number in the numerator except for 4. In the bottom one, the parentheses say, hey, keep 4 times 3 times 2 times 1 in the denominator. So it's definitely the bottom one. I've seen that happen a lot in previous semesters. Definitely want to keep parentheses around your numerator and your denominator when order does not matter. When order does matter, you're dividing by 1s, so it doesn't, 1s aren't going to do anything either way. It's definitely this number, not the top. Additionally, now part B, they're asking about the defective calculators. So is that going to affect the number of calculators? Or the number of dashes, rather?
Not the number of options.
So they're still sending out how many of these selections. It's still 4 calculators that are being sent, not the 4 that are defective. These are the 4 that are being sent. We haven't used the defective part yet. How do we use the defective part in this problem? Anyone happen to see it? So what's going to go in the first blank? 36. 36. 40. So 4 of the calculators are defective. But they want to know not defective. Well, 4 of the 40 are defective. How many are not defective? The other 36. That's where 36 is coming from. If 4 of them are defective out of 40, then 36 are not defective out of 40. And repetition still cannot happen. So then it's 35, it's 34, and it's 33. And order still does not matter. Put this in the calculator. If you have one of the fancy calculators, I think it spaces everything for you. If you have one of the simple ones like this one, definitely it's encouraged you use parentheses. And you should get 58,905. Does anyone have any questions? If not, let's move on to example 10. So, Baskin-Robbins, fairly popular ice cream vendor, is known for its 31 flavors. Determine the number of 4 flavor options. Okay, so how many 4 flavor options are possible? I guess, how many dashes do we start off with? It's 4, the flavors. Obviously, it's not 31. So 1, 2, 3, 4. What numbers go in them? Well, there's only one number left. It's the 31. Not really too tricky of a problem. So start off. So if you're, I don't think I've ever been to a Baskin-Robbins before. I'm guessing there's this see-through glass and you can just point to various ones. So you point to the first one out of 31 options. And then once you pick that one, assuming that they make you pick different flavors to do the 4 flavor option, means you can't repeat. And since you cannot repeat, just go down. For each one you pick, you cannot repeat that ice cream flavor that you chose. So it's just one less option you have available. Does the order matter? Order does not matter. Well, unless you just genuinely want your ice cream flavors in a certain order. But order doesn't matter. Then when order doesn't matter, you start off with 1 and you work your way up. Do that every time order doesn't matter. You just keep climbing, adding 1 until you run out of spaces. Just so happens the ones that we have done only have 4 spaces, so we only went up to 4. If it had 5 spaces, we'd go up to 5, and so on and so forth. Okay, let's figure out this one. So 31 times 30 times 29 times 28 4 times 3 times 2, I think that's just 24. 3, 1, 4, 6, 5. 12 times 2 is 24, yeah. Okay. So that's how many 4 flavor options there are available Baskin Robbins. Everyone's good with that? Go ahead and do some more. There's a multiple choice test with 5 questions, and each question has 5 possible answers. So perhaps you've been in the situation where you're taking one of the Scantron tests, you're running out of time, and then you just mark randomly for the remaining Scantron ones. I think when I took a standardized test in high school, I just marked AC/DC for all of them because I didn't care when I was in high school. But now this is going to show what is your likelihood of getting all of them right, in essence. How many different combinations are there for marking the Scantron questions, if there's 5 of them, A through E or something like that? So we start off with, well, how many dashes do we put? I'm seeing 5s just scattered all over here. Okay, 5 dashes. The question is, where's this 5 coming from? Is it the 5 questions, or is it the 5 possible answers? It's the 5 questions. So each one of these represents an answer that you're choosing on your Scantron. So you could have chose A, D, B, E, B. So how many choices do you have for each question? Well, for the first one, you can choose any one of them. You could choose A, B, C, D, or E. What about the next one? That's 5. You can repeat. You can pick A for all of them. You could pick D for all of them. You can repeat. Does order matter?
Yeah.
This one matters. You choose A for the first problem and D for the last one, then, well, really, if order didn't matter, that would kind of work in your favor. You just picked A, B, C, D, E, and then they just permuted it and mixed and matched as you needed. You probably would do much better. But order matters, because for each question, there's a specific answer that corresponds to it. Order matters, which means we have all ones. So that's just 5 to the 5th power, whatever that is. 3,125. So you have a 1 out of 3,125 chance of, if you just mark in 5 questions at random, 1 out of 3,125 people will actually get them, all 5 of them right somehow. And I'm guessing you all know the rumor, when in doubt, mark C for all of them. I don't know if you've heard of that. Statistically, C is the most frequent answer for Scantron tests. So. Okay. Example 12. This one's a little tricky. How many tickets with different points of origin and destination can be sold on a bus line that travels a loop with 23 stops? This one's given some people confusion in previous semesters. So I'll pass the question off to you. How many dashes do we put? It's 2. It's 2. You might think, where's 2 coming from? So the 2 represents origin and destination. This one's a tricky one. That's definitely a tricky one. It's origin and destination. So those are the 2 dashes. So now the question is, what goes into the dashes? Well, how many points of origin are there? Well, there is another number in the problem.
3.
It's going to be the 23. You have 23 different places of origin because there's 23 stops. Any one of those stops can be a point of origin. And then your point of destination. Is that going to be 23 or 22? Different points. Different points of origin. Can't repeat. 22. Kind of a tricky problem, but this is the best way to think about it, in my opinion. 23 points of origin. You have to have different points between the origin and the destination, so that limits you by 1. And then does order matter? Order matters. If it didn't matter, then your point of origin, your point of destination can be swapped. And perhaps that may make your commute a little bit tumultuous at best. The place you start at is now your destination, but you're already at your place of origin. I don't know. Order matters though. And it's just 23 times 22. $506. Does anyone have any questions before we look at another problem? Okay. Example 13. License plate is to consist of 3 digits, 5 uppercase letters. Determine the number of different license plates possible if first and second digits must be odd, repetition is not permitted. Okay, so it seems like everything's been leading up to this problem. That sounds like could be tricky, or may not be. It's a counting problem, so we know we can break this down into 3 steps. How many dashes do we have?
8.
It's going to be 8. 3 digits and the 5 uppercase letters. We have 8. 1, 2, 3, 4, 5, 6, 7. Determine the number of different license plates possible if the first and second digits must be odd and repetition is not permitted. Okay, it's kind of interesting. So the first and second digits must be odd. Well, odd numbers. 1, 3, yeah, it does say odd. 1, 3, 5, 7, 9. There's 5 odd numbers. 5 odd numbers, 1, 3, 5, 7, 9. Well, that seems to tell me pretty clearly how many options I have. If anything, if the first digit has to be an odd number, then that's 5 options. Five odd numbers. This is a reminder where the 5 is coming from. Okay, so first digit, there's 5 options because there's 5 odd numbers. The second digit must also be odd, but repetition is not permitted. We lost 1. because repetition is not permitted, but we still have to be odd. So still have to be odd. So the next digit, it starts off at 5, but then it says, hey, you can't repeat. Okay, well, I chose one from the first slot, so that's 4 left. And then for the next digit, it's 8. Yeah, it's not 3. It's 8. And I think where's 8 coming from? I thought we had a good thing going. It was just going down by 1. It's digits, right? The third digit doesn't have to be odd. It doesn't say anything about the third digit having to be odd. Third digit can be whatever it wants to be. So you chose an odd number for the first one. You chose an odd number for the second one. The third one could be any number, which starts off with all 10, but those 2 odd numbers you chose are gone. That leaves you with 8. That takes care of the digits. Now we move on to the 5 uppercase letters. What does it say about the letters? The first and second digits must be odd. All right, we took care of that. And repetition is not permitted. Well, it goes into those next spaces. From here, it's just how many letters are there in the alphabet. It starts off with 26, but since repetition is not permitted, we slowly lose 1 each time. And then finally, does order matter? Order does matter. These are license plates. The arrangements of the letters and the digits will distinguish one car from another. So order matters. Which means you just put a bunch of 1s. Or in other words, just multiply the numerators. Five times 4 times 8 times 26 times 25 times 24 times 23 times 22. A rather large number. Okay, to answer your question, we have the 8. So you're referring to the 8 right here. It's because the first 2 digits had to be odd numbers, which there's only 5 odd numbers. So we choose 2 of the odd numbers. And now to answer your question why there's 8, the third digit doesn't have to be odd. Because it only says the first and the second digit have to be odd. But the third digit, it doesn't say anything about it. So that means there's 10 available options for the third digit. It can be even or odd, it doesn't matter. But we already chose 2 of the odd numbers for the previous problem, or the previous 2 digits. It just so happened they were both odd numbers, but they're still numbers nonetheless. And that's what leaves us with the 8. So what number did I get here? 1, 2, 6, 2, 9, 7, 6, 0, 0, 0. Rather large number. So that's how many combinations there are. So 1 billion. 1 billion plus 1.26 billion. Does anyone have any questions up to this point? If not, what I'm going to do is start going over the workbook assignment. So we have 15 minutes left. So if you haven't jotted down the workbook assignment already, I'm going to rewrite it here in a second. So If you didn't jot this down, workbook number 3. It's page 10, numbers 1, 2, 3, and 4. Page 11, 1 and 3. And that's due Friday. Let's see how many of these we can knock out before we run out of time. We'll start off with page 10, number 1. And so what this says, U is 3, 7, 11, 15, and they put a bunch of dots that means continue in this order all the way until you hit 27. They also tell us that A is just 7, 11, and 15. And they tell us that B is 3, 11, 19, 27. And they want us to figure out a few things about these sets. So this is going back to sets now. So this is the previous section we talked about. So it wants us to first figure out A intersect B. That's what that upside down U represents. It's the intersection. This is a reminder, that's the intersection. And the intersection means and. Everything that's in A and B, or in other words, what do A and B both have in common? You have a question? Oh, okay, gotcha. Okay, so A and B, just the overlap. What do they have in common? Simply just looks like 11. Looks like they just both have an 11 in common. So that's what the and represents. You still have to use that curly brace notation because it's a new set that's based off of comparing the old two sets together. So it's just a set containing 11. Because that's what they both have in common. So that was the first one. The second one is the union. That one is and, this one is or. The union just means, I don't care if it's an A or B, just give me everything. Okay, so in A, I see a 7, I see an 11, I see a 15. All right, I'm out of stuff in A. Let's jump down to B. I see a 3, I do see an 11, but we don't repeat in sets. We don't have to write that down twice. So I'll skip it. I'll go to 19 and then 27. And I'm out of numbers. So we just don't write down any duplicates. Next one is A with that apostrophe. So this is that's the complement. So really that's the complement. So the complement, it's everything not in A. So you might think, what does that mean? Everything not in A. So remember, the complement is everything in the universal set that is not, or everything in the universal set that is not an A. So the universal set is the one at the very top. So everything in the universal set that's not an A. So it's a new set. All right, A has 7, 11, and 15. I'm just going to write down every number from the universal set that's not 7, 11, or 15. There's a 3. And what's the next number I'm going to write down?
19.
What's that?
19.
It is 19. It's 19, so those dots, so what those dots mean is to continue that pattern, these are increasing by 4. So 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and there's a 27. So that's what those dots mean. It's basically saying there's a 19 and a 23 in there as well. So 23 is not an A, and 27 is not an A. So that's where that's coming from. That's what those dots mean. So I've seen a few semesters, students will misinterpret what the dots mean and they'll just normally ignore it. So let's look at B complement. So same idea, just everything that's not in B. B has a 3, so of course that is in B. There's a 7 in the universal set. So basically I'm reading off the universal set and I'm going to write down everything that's not in B. So 3 was in B, so I don't write it down. 7 is not, so I write that down. 11 is in B, so I don't write down that. 15 is not in B. 19 is in B, so I don't write it down. 23 is not, and 27 is. So that's how I get those numbers. Does anyone have any questions about this one? Might be able to fit the second problem off to the right here. This one asks, how many ways can you line up 5 books on a bookshelf? Okay, how many ways can you line up 5 books on a bookshelf? 5 books on a bookshelf. So this sounds more like an accounting problem. It's the number of combinations. How many books can you set up on the bookshelf? So how many dashes do we put? Imagine 5. This is one of those interesting problems where the one number sort of represents not only the number of dashes, but also represents the quantity that goes into it as well. 5 books means there's 5 different places for the books. How many options do you have? Well, how many books do you have? The 5. So you have any one of the 5 books that you could place, I'm guessing, on the far left. But of course, you can't repeat the books. So you lose the number, I'd like to not do that. 3 and then 2 and then 1. So that's how many combinations you have. And then you ask yourself, does order matter?
No.
Does order matter? I feel like order matters. I don't know why. I think order matters, but this is a workbook problem. It's not really a big deal. I grade these, so I don't know. I think it matters. I mean, what about if you arrange the books in alphabetical order? Then switching the order, does that alignment still stay true on the bookshelf? That's probably the counterexample I think of in mind why I think order does matter.
If it didn't matter and you divided it, would it come out to be less? You're dividing every number, would you do 5, 4, 3, 2, 1?
That's a really good way of explaining it.
There's obviously more than one way to rearrange the book.
That's a very logical way of thinking about it. If order did not matter, then you would divide 5 times 4 times 3 times 2 times 1 by 5 times 4 times 3 times 2 times 1, which means there would only be one way to arrange 5 books on a bookshelf. And you probably think to yourself, well, what about if I just switch 2 of them? Isn't that a new combination? Yeah. That's a way you can think about it. I like your way more. Order matters. 5 times 4 is 20, 20, 40, 60, that's 120, I believe. Five times 4 is 20, times 3, 20, 40, 60. 120. Cool. So it's just 120. Everyone good up to here? Okay, let's look at number 3. How many ways can you line up a family of 4 for a picture if the youngest insists on being on the far left? There's a family of 4. And youngest on the far left. All right, how does that change things up? How many dashes do we put? 4 people in the family, 4 dashes. 1, 2, 3, 4. How many options do we have for the first one? It's 1. 1 option. If one person has to be on the far left, he wants to be right here. So that's 1 option, the youngest child. And then from there,
It doesn't matter.
it's 3, 2, and 1. So basically after the first position is fixed, then the remaining 3 family members can kind of figure it out as they please. Which means one of the 4, he's fixed on the far left, your left, and then remaining 3, it goes down from there. So it's just 6. And of course, order matters. Because of course it matters, the youngest wants to be on the far side. And if it didn't matter, you would get a decimal. Because you would divide 6 by, yeah, you'd divide 6 by 24. It means you get a 0.25 number of combinations, which, if I did that math correctly, 24, yeah. All right, I think we can fit in one more. Number 4, how many different 3-digit area codes are possible? So number of 3-digit area codes. Well, maybe the number of dashes, maybe apparent to somebody.
3.
3 dashes. You all know hopefully how area codes work. 985 is the common one. And what numbers go into them?
You would have 10 options each time. It
Just-
doesn't say that they can't be repeated.
No, we can have any 10. Or 0 through 9, 10 options. And so that's just a thousand. So that's the first page of the workbook assignment. So we'll make things a little bit easier. So that means you have until Friday to do the other 2. But I'll wrap it up here. Be aware of the new due dates. Push some stuff back. And that's all I got. Have a good day. Rolls over on the side table.
Why did you decide to stop posting the